So today we will see as to how hole conducts electricity in the valence band. But before we do that, let me very quickly summarize what we studied in the previous class. That is, how a material becomes, when a material becomes metal, when it becomes an insulator, and when it behaves like a semiconductor. So for metal, these are the inner electronic levels, and this is the outermost energy level, which when atoms are stacked together to form a solid, a crystal, then the outermost electronic level actually becomes an energy band. Now for a metal, the outermost energy level, which has now become a band, is actually partially full. And that is why, upon application of a very small potential difference, these electrons can conduct electricity, allowing a flow of current in the metal. So in a metal, if you just apply just a reasonable potential difference, small potential difference, it will result as a flow of current in a metal. The reason for this is that the outermost energy level, which has become a band, is actually partly full. So this is the metal. Now, what is an insulator? An insulator is again, the inner electronic energy levels are discrete, they don't form band, and the outermost energy level, which forms a band, energy band. For an insulator, this is completely full. So this is called a valence band. And the next energy level is located at with an energy gap which is extremely high, several electron volts, many electron volts. So this is the forbidden energy gap. So if an electron can be made to cross this barrier and appear in this conduction band, then of course it will conduct electricity. But this forbidden energy gap is so much more, so enormous, that it is impractical to make an insulator behave like a conductor, behave like a metal. The thermal energy that is associated with these electrons in the valence band is too small to allow the electron to cross over to the conduction band from the valence band. This is the conduction. And if you have to apply an electric field so that the electron can experience enough force to cross over to the conduction band, the field required is several millions of volts, several millions of volts per meter, which is quite impractical. So what is a semiconductor? For a semiconductor too, this is semiconductor. For semiconductor too, the valence band, just like an insulator, is completely full. But interestingly, the conduction band lies here in the immediate vicinity of the valence band. So that very little energy, with very little energy, the electron from the valence band can jump over to the conduction band. So if you look in terms of the orbits of the electrons, the valence and this conduction band, so this is the nucleus and this is the valence band orbit. So the conduction band orbit is lying very close to this valence band. This is the, so with little force, this spacing is so small, it's a delta X. The difference in the radius of these two orbits. So this is R1, this is R1, and this is R2. R2 minus R1 is very small. It is the delta X, very small, so small that with just little force or little field, the electron can cross over from this orbit to this orbit. So that is why even say at very low temperature, the electron energy may not be enough to cross over from valence band to the conduction band. But at slightly elevated temperature, set room temperature or slightly more than room temperature, a fraction of the electrons from the valence band can actually cross over to the conduction band. And therefore, it can conduct electric current. But interestingly, in case of semiconductor, it is much more interesting compared to a metal, because in a metal, the conduction occurs only due to flow of electron in the conduction band. But in a semiconductor, the semiconductor, as an electron crossover from the valence band to the conduction band, the electrons appearing in the conduction band would of course conduct electricity, but the gap that the electron leaves behind in the conduction band, which is called hole, can also result, this motion of holes in the valence band also contribute to the flow of current. This is what makes a semiconductor much more interesting compared to metal. So today we go a little deeper and see as to how hole conducts electricity, flows, how the motion of hole in the valence band conducts electricity. You see, in reality, however, holes do not move by themselves, but appear to be doing so as the valence band electrons basically engage themselves in a game of musical chairs. Let us see as to how does it happen. How do we say that the valence band electrons basically play a game of musical chairs, and which allows the motion of holes. So this point can be readily understood by referring to this figure, which essentially represents a collection of snapshots of the motion of the electrons in the valence band captured sequentially in time. So starting from, say, if this is at time t1, t2, t3, t4, t5. So first is t1, then t2, then t3, then t4, then t5. Sequential. The motion of electron have been captured in this. So following the creation of this hole, see the electron which is present here, it jumped up, and this is suppose the conduction band. The electron jumped into the conduction band and created a hole here. The electron has gone. This electron. So this electron has gone and a hole has been created. In the valence band, one of the neighboring electrons that is either this electron or this electron, determined by the application of the voltage. So that whether the voltage has been applied, see, this is the block of semiconductor, whether this side is net positive or this side is negative and this side is positive. Depending on the polarity of the field applied, one of the neighboring electrons, whether this or this, decided the polarity of the applied field, moves quickly into it, thereby creating a hole in its original location. So either this electron moves and occupies this place, or this electron moves and occupies in this place. It would depend on the polarity of the field applied. So for example, let us assume that this electron moves. So as this electron moves and occupies this place, it creates another hole in its original place. This electron has moved here, so a hole has been created in its original location. And as a second electron now moves to fill this new hole, a second electron now moves to fill this new hole. So another hole has been created in its location. It leaves behind yet again another hole, and so on. In a nutshell, therefore, the motion of the whole moves in this direction, from here to here to here. The whole is moving in this direction. So motion of the whole occurs in a direction opposite to that of the electron. While the electrons are moving in this direction, holes are moving in opposite direction. Thus, in a semiconductor, the flow of current in the valence band can as well be thought of as originating from the motion of holes instead of the electrons. So the motion of the electrons actually is responsible for the motion of these holes. Now this hole-centric approach is also inherently simple to analyze because you only deal with one hole. This hole is moving. As in the valence band, there are only fewer holes that are greatly outnumbered by the electrons, while there are many electrons. For example, here we have only one hole, but there are so many electrons. So this hole-centric approach is also much easier to analyze. Now you see, semiconductor materials exist both in elemental and compound forms. An atomic semiconductor as well as a molecular or compound semiconductor. Like an atom has its own electronic energy state, a molecule too, as we know, will have its electronic energy levels. And like in an atom, the outermost electronic energy level can be broadened when many atoms are stacked together for forming solid. Same also happens for a compound, a molecule. When they are stacked together to form a solid, the outermost electronic energy actually gets broadened energy, forming an energy band. So we will have both semiconductor both in elemental as well as in compound form. Now some of the two most popular element-based semiconductors are silicon and germanium. And some of the molecular variety of semiconductors that find wide application are gallium arsenide, gallium phosphate, indium phosphate, etc. And as a matter of fact, gallium arsenide and indium phosphate are the most widely used materials for the operation of semiconductor loops. That is what we're going to study in this course. Now, both these varieties of semiconductors are also called intrinsic semiconductors, as the semiconducting property are inherent to this material, as we have just seen. In case of semiconductors, the conduction band lies very close to the valence band, and this is intrinsic to the property of the semiconductors of both varieties, that is the atomic semiconductor as well as the molecular semiconductor based on compounds. By virtue of their ability, semiconductors allow the conduction of electricity by both electrons and holes, displaying remarkable properties, like the presence of only a trace quantity of impurities can significantly enhance the conductivity of semiconductors. Let us explore it even further. So semiconductors embedded with such impurities are called doped or extrinsic semiconductors. While varying the concentration of the dopant in a semiconductor allows ready tailoring of the conductivity, careful selection of the dopant material will allow selecting the type of majority carriers, charge carriers. The extrinsic semiconductor, for which electrons are the principal charge carriers, are called N-type semiconductors, while the semiconductor with holes as the majority charge carriers called P-type semiconductor. We will come to it and study it in more detail just in the next slide. And just for sake of interest, a semiconductor reveals its true potential when a p-type semiconductor and an n-type semiconductor are brought in contact with each other. Interesting effect originating from the passage of the charge carriers through this junction bring about the operation of a variety of semiconductor devices. The p-n junction diode being the simplest of them. Our focus will be on the physics in the next few lectures. Our focus will be on the underlying physics that allows operation of a semiconductor diode as an emitter of both conventional and laser light. That will be our focus. So we take a deeper look on the extrinsic semiconductor, that is N-type and P-type semiconductor. You see, a silicon atom, which is of course an intrinsic semiconductor, has 4 electrons in its outermost shell, and they are individually bonded to the electrons of the adjacent atoms while forming the crystal. As you can see here, the semiconductor, each semiconductor atom has 4 electrons in its outer shell. And when they form a crystalline silicon, each electron actually is bonded to the electron provided by the adjacent silicon atoms. So in the absence of any loose or free electron, the silicon crystal will not conduct electricity because its outermost shell is full. Unless some electrons from the valence band are excited to the conduction band, either thermally or by some other means. So basically, the valence band is completely occupied. All the electrons are bonded, and so it would not conduct any electricity. However, the conduction band, the next available energy level, is so close to the valence band that with just little thermal energy, some of the electron can make a transition to the conduction band. So this is intrinsic semiconductor. Silicon is an intrinsic semiconductor. So it shows this semiconductor. But let us see what is N-type semiconductor. When silicon becomes an N-type semiconductor. You see, however, doping of this silicon crystal with just trace quantities of arsenic. In what ratio? In a ratio of about just 1 arsenic atom in about 100 million silicon atom. So the ratio is 1:100 million. It is so insignificant, this doping concentration, but it can bring about remarkable changes in the electrical conductivity of this dopant silicon when it has been doped by arsenic atoms. in this ratio, 1 is to 100 million. That is, every 100 million silicon, there is only one arsenic atom that can remarkably change the electrical conductivity of this material. As a result of doping, the arsenic atoms will replace silicon atoms at a few locations in the crystal. Arsenic has 5 electrons in its outermost shell, of which then 4 electrons will be engaged in forming bonds with the nearest silicon neighbors. Silicon has 4 electrons in its outermost shell and argon has 5. So you can see that 4 of arsenic atoms will make bond with 4 of silicon atoms in the neighboring silicon. Now one of the atoms, electron of the arsenic, it has 5 electrons, will be free to move. So the remaining electrons being loosely bound can therefore move freely in the crystal. The arsenic atom thus functions here as a donor of electrons that can easily get into the conduction band because it is free to move. It is not particularly bound to any nucleus. And it being the outermost electron of arsenic atom. The majority of the carriers in the this semiconductor, extrinsic semiconductor, are there for electrons, and hence the name N-type semiconductor. So in this semiconductor, the majority of the charge carrier is electron, which is provided by this arsenic atom. And that is why such an extrinsic semiconductor is called N-type semiconductor. The few holes that are present in the valence band owe their origin to the direct excitation of a few electrons from the valence to the conduction band. That is the intrinsic. This is the silicon is intrinsic semiconductor. So the few holes that you see are created in the valence band. That is because this gap is so small that even some thermal energy, as we know, can make this electron from the valence band to cross over to the conduction band. So these few holes that you see here, the few holes that are present in the valence band owe their origin to the direct excitation of a few electrons from the valence to the conduction, but the intrinsic property of the silicon semiconductor. But the majority of the charge carriers that you see here that come from the donor arsenic, and this is called N-type semiconductor. So it is needless to say that most of the electrons in the conduction band have been donated by arsenic. So let us see now what is a p-type semiconductor, where the majority of the charge carriers are hole instead of electron. You see, doping the silicon crystal with trace quantities of gallium atom, on the other hand, results in a totally different behavior. Instead of arsenic, if we dope the silicon crystal with trace quantities of gallium atoms, it will result in a totally different behavior. So let us study. A gallium atom has only 3 electrons in the outer shell, and as before, they will replace silicon atoms at a few locations in the crystal. So here, so gallium atom has replaced a silicon atom, and gallium has 3 electrons in its outer shell. So if it has to make bond with 4 silicon atoms, then it will need to have another extra electron. So this, it is not difficult to perceive that as a gallium atom gets electronically bonded with the neighboring silicon atoms, a hole will be formed where the 4th electron should have been present. This electron should have been present here, but this electron has gone here. So we can say hole has been created. And this hole basically is supplied by gallium atom. As already explained, these holes will conduct electricity in the valence band. The hole has been produced at the valence band. And so, these holes will conduct current in the valence band, just like electron conducts current in the conduction band. Now, the majority of charge carriers here are thus now holes. And accordingly, this variety of extrinsic semiconductor is termed as p-type semiconductor. The few electrons present in the conduction band originate from the thermal excitation of some electrons from the valence band to the conduction band. This is just the intrinsic property of the silicon. The band gap is, forbidden energy gap is so small that even with thermal energy, some electrons can actually cross over from valence to conduction band. So the few electrons that you see in the valence band, it actually resulted for direct transition of electrons from the valence band to the conduction band. But most of the holes that you see, maybe only 2 holes have been originated from this transition, but the remaining holes are all contributed by the dopant, that is the gallium atom. The gallium atoms thus function here as an acceptor of electrons, making the movement of the holes possible in the valence band. So this is the band structure of a p-type semiconductor, revealing clearly that holes are majority charge carriers here. So that is basically the extrinsic semiconductor and how the majority charge carriers in case of n-type semiconductor, extrinsic semiconductor is electrons, and for p-type semiconductor are holes. Now, let us quickly see what is a semiconductor diode. You see, joining together the p and n-type semiconductors adds a new dimension to the semiconductor, paving the way for the device application. Now, we need to take a deeper look at the working of a p-n junction and see the behavior, the very interesting behavior of this junction, which is formed when an n-type semiconductor and p-type semiconductor are joined together. Left to itself, some of the free electrons from the n region will diffuse towards the p region, and likewise holes from the p region will diffuse towards the n region. And as they meet at the junction, the electrons jump into the holes and both carriers disappear, understandably so. This leaves in the immediate vicinity of the junction layer, in the junction, a layer of positive charge in the n side and a layer of negative layer in the p side. I think this is clear. The charge separation between the positive and negative ions sets off a field that opposes any further diffusion of charge carriers across the junction. So this negative layer actually prevents any more electrons from the n type to diffuse into the p side, or holes, or this layer of positive charge prevents any diffusion of hole from the p side to the n side. This results in establishing a thin region in the vicinity of the junction that is devoid of any charge carriers. There won't be any charge carrier, either n or p type, hole or electron. And this region is called a depleted region, opening up the interesting possibility of using the p-n junction as a diode. So I will end today's lecture here and begin right from here and see as to how the formation of this depleted layer results in performing the ability of this p-n junction to work at the time.